So we are going to get started. Thank you all for joining again today. Today we're going to today is one of our 1-hour webinar series on. Today we're going to be specifically talking about our devil in the details components and looking at the specific component of insulation as part of that devil in details series. Is really looking at it more from a what are common things that get overlooked or become that devil that kind of keeps poking itself out in our construction documentation. And so we thought this would be one of those conversations. We do a variety of them, but insulation is again one of those things that we sometimes get confused on how it's operating. And so we thought we'd take time to kind of drive home that conversation as to what we're looking at. Let me reposition my camera. So again, this course is being offered as part of the Minnesota Energy Code Support Program, our collective program created by the utilities that service much of the state to help building professionals construct buildings that are both energy efficient and benefit their communities in our environment. So really, it's all about just ensuring that we get building code compliance, and that's really our focus. And so hopefully you can see mine. Let me double check this. Oh wait, lost that. Let me see. Nope, I didn't turn on the chat. So you should be able to use the chat feature now. Can you guys just a thumbs up? Can you see the screen? Can you see my screen? Perfect. Thank you very much. I did something. I clicked something on Zoom, and so now it's like giving me some weird looking stuff going on. So it's a little freaking me out, but I'll be okay. So again, when we talk about what is the building compliant, so the purpose of the program is obviously to again educate, provide training, free training resources to you as building officials throughout the community, as well as your contractors and things of that nature. So again, we have a website that you're more than welcome to go to anytime. Review. It has a list of all of our upcoming trainings, some of our technical resources. That's where we're going to be putting our videos of these trainings. Probably in the next by Monday is the deadline that I put out there for that, as well as some different ways to contact us, ask questions through our code helpline. So it's a great resource, and again, it's something that we're going to be here for at least the next 3 years. And if history is any indicator, it's going to be much longer than that. But we're here to help you, and we've got some ideas about what we might do next year to even make it a little bit more dynamic and helpful for you as a community. But one of the things that I've always kind of hit on, and if you've participated in any of our trainings up till now, you've heard probably more than once, is when we understand the why behind a question, we can figure out the how to get it done. That's one of those core principles that I've kind of thought just really is helpful to understand and reinforce when we think about what we're doing here today. And as part of that conversation, we are going to look at the why of the building code. The why we have a building code is because we're trying to provide some basic uniform standards for construction. We want to make it, again, for those minimum expectations when a person builds in the state of what do we expect in our communities. And part of that is understanding that we're including a desire to see construction. And when we think about all the tag groups that are going on lately, we're sharing it, it's not showing up. Not showing up. Okay, let me double check. Share screen. Is that better? Thank you, Jesse. I thought, like I said, Zoom's messed with me a little bit. So, but again, just real quick, I'll go back over those quick slides. So again, we're here to help. We have a website, and we understand we need to know why we're here. And we're here because there's basic requirements, and that we want to make sure that our buildings are constructed to be efficient and operate successfully over their useful life, right? We're not looking at a short-term expectation on these buildings. We're looking at them for the long-term, the lifelong expectancy of our buildings. And so that's part of that expectation. We want to mitigate heat loss, control energy. The code is all about control. And when we think about those standards, and we think about how they apply across our projects, they apply to new buildings, new portions of buildings, new equipment, new systems, alterations, additions, changes of occupancy, all these different situations that now that fall under, not now, but fall under the scope of the energy code, because we're really thinking about how does a building operate. It's not just about how do the 2x4s sustain the loads that we place on them. It's more about the total realization that a building is going to last for a period of time, and we need to make sure it's built efficiently. So, with that being said, what this particular code does not address, again, we understand are those residential components, those residential occupancy types, and again, that's when the residential code pops in. So again, that's another conversation we're talking about there. When we think about mixed occupancies, we understand that if it's more than 3 stories, then it's going to fall under the commercial provisions. If it's if it's 3 stories or less, and it's an I1, R1, R2, R3, R4, then again, we're going to go back to that residential. So it's basically what we understand from the IECC, but just it's applied to us in this because now we've dropped off the IECC and we're using the ASHRAE 90.1 2019 as our base code for the state. So today we're going to look at it from the perspective of energy compliance, right? We're going to look at what are some design, when we think about, again, this is design and this is the details of the devil in the details series. And so we're really looking at the project or this issue of insulation from a design perspective, from a plan review perspective. And we understand that when we think about designing a building for energy compliance, we're looking at 4 key components. We're looking at building thermal envelopes, mechanical systems, surface water heating systems, and power and lighting expectations or provisions. Right? Those are the basic things we really think of when we think about what does it mean to be energy compliant. And specifically, we're going to focus in more on this concept of building thermal envelope. Now, in chapter 4, we get into the concept of enforcement. And in that chapter, we get things like the expectations for what should be on our construction documents. That's that list of things like, energy compliance paths, as well as insulation, fenestrations, U factors. Because remember, the building thermal envelope is that component or series of components that separate conditioned space from unconditioned or semi-heated spaces, right? So we're isolating, we're controlling that conditioned space within the building, and that could be in a variety of different systems. It could be in wall systems and windows and those kinds of things. And so that's why these components all make up that building thermal envelope. It is one of those, to me, one of the most important things to remind ourselves of is the building thermal envelope. There's one thing my family hates to hear is the word building thermal envelope, because they hear it so much that they're like, we understand it. Surely everybody else does. And that's one of those realities. It's one of those systems that really can drive or bring a project to success or to failure. And very quickly, and I don't want you to read these, you're going to get a copy of these slides, but it's more for just a reminder that when we talk about those compliance paths, that prescriptive, energy cost, and norm in Appendix G, those 3 expectations, right? The expectations when we build a new building is that we're going to follow one of those 3 options, right? A, B, or C. And that we're also going to expect there's going to be compliance documentation, the materials are going to be properly installed, we're going to do inspections, and it's going to be commission tested or verified, right? Those are the expectations of every project that's a new building. Same of 3 apply. The same expectations apply whether we're talking additions, and again, there are exceptions when we talk about additions. When the addition cannot comply with itself, we can do some modeling to make sure the energy consumption is there. So again, if it's not going to work through the prescriptive, then we're focused on the other compliance paths. Alterations, again, this red section here is the addition that the state put into the model language that was in the code, and really, again, it's telling us that and when we're talking about alterations, that they're going to conform to the new construction standards when we're not altering other components, right? That we need to treat them as that alteration, not the whole building, right? We're making sure we're scoping the project appropriately. And then when we're talking about existing buildings, again, we know there's an exception for historic buildings, and that they have to do the best they can, comply to the greatest extent possible. We're going to have specific conversations about historic structures. One of the things that we see here is the concept of historic, when we look at it in the way it's defined, is, it's really the part, the onus is on the design professional to demonstrate why it's historic. The actual, is it registered? Is it a local district? Those types of qualifications. Again, when we talk about change of occupancy, we're going to require that they comply with Section 9 for new lighting, right? Because we're making sure that that building, even if we're doing some simple things to that building, we're making sure we're thinking about how that building is going to operate for the lifetime moving forward. So again, those are some scoping things, but really what we get is this concept that there are 3 basic compliance paths, right? There's going to be the prescriptive, which is follow the tables, do what the code says. The energy cost budget, which is going to be that how much does it cost to operate versus the similar size building of a standard design. So it's going to be that 1-for-1. We've talked about compliance paths before. And we also have that normative G, which is going to be that performance rating. How does it perform compared to a standard structure? And so again, we're going to evaluate those systems, and it's really critical to understand which compliance path we're utilizing, especially when we talk about insulation, because that's going to tell me how much deviation and flexibility I can have when it comes to the way these materials are designed. Remember, when we talk about compliance paths, we also talk about, from a thermal envelope perspective, compliance that's both prescriptive or the building trade-off compliance path. Now, the trade-off, so the prescriptive, if we look at it very quickly, again, prescriptive is going to be taking that table, whether it's for climate zone 6 or 7, and applying that table. U factor, R value, boom, we're done. These are the maximum minimum values, depending on what we're talking about, and that's what you have to have. The trade-off, which is when you're going to start talking about things like ComCheck or some other energy rating, energy calculation analysis software, that's when we start looking at the building as a whole and start really doing the math behind calculations to determine, is this building thermal envelope still going to be compliant? So you get a level of flexibility there that you don't see if I'm going straight, I call it straight prescriptive, right? So there's prescriptive, straight prescriptive, and there's building trade-off. And then you get into building energy, cost, and building performance, right? So there's 4 options for a project to follow. The one I typically see the most is going to be ComCheck, this building trade-off, because it's just a free software that's easy to manipulate. Now, we'll do a deeper dive into ComCheck later. I think that's one of the things we talked about yesterday. I think ComCheck is a great tool. This is the old ComCheck, legacy ComCheck, and you could go through that process. And you can also follow the new ComCheck. Now, ComCheck, again, is a free software ran by the Department of Energy. Anybody can log in, get a free password and email, develop your own. As a building official, as a designer, whatever, you can do this. There's no registration fees or anything. This is a free software. And we have confirmed, we've gone through as much as run the test as much as we can internally through ComCheck, and we've corrected some, identified the bugs. They've fixed the bugs that we identified. And so Minnesota is listed as a specific code in ComCheck. So when you log in and you go to that first section in this drop down, you'll be able to select, it's at the bottom of the list, the Minnesota 2024 commercial code. And so it'll apply all the values, all the specific amendments that are reflected through this calculation system are in that series of tables. Very, very, very quickly, I want to show you this very quickly, the system. So you would type in some type of value for your community. Again, you're going to get as close as possible. Most of the county's largest cities are in there. So again, that's going to give it all the background details on elevation, heating, cooling design days, all those different variables. You're going to tell it, what type of construction. Are we doing an alteration, addition, a new construction, right? You're going to tell it, we're going to define some types of values, right? On building area, are we talking about, especially when we think about commercial, are we talking about retail versus storage versus office versus, all those different categories that we find within the energy code. And then we're also going to be able to go into it and start applying envelope features. That's where you're going to start to design concepts like, am I going to look at insulation? Am I going to create a roof structure? And what kind of roof am I going to put into that? And you'll go through the process of actually developing a building, right? I've already done a lot of the work on this one here. And so you've got a building that's going to show all of the relative components, the size of the area, as well as, are we looking at cavity? Are we looking at continuous? What's the potential U factor if it does that mathematical calculation based on some of the variables that we see here if we're doing steel frame 16 on center? It does all the math to tell me what that U factor is going to be. Some people utilize this to get to a U factor. You can do that, or again, you can, at the end of this process, you tell it orientation. That way it can affect, as it may affect certain calculations and certain variables, especially when we talk about window glazing and the impact of solar heat gain on a window. So you can see some of those variables listed there, whether we have doors, swinging doors, those sizes of the doors. All of this information can go into ComCheck, and then you'll run a quick report, and then that report will spit out a compliance document, right? That compliance document, if you've done ComChecks before, you're usually looking for that green bar that says it passes, right? This is where we're going to find that green bar, and that's, and for a lot of people, that's the end of the story. It's not, right? But you can clearly see where it's identified what those cavity and continuous values are for that particular system, right? Remember, when we talk about the building thermal envelope, we're not talking about the building wall envelope. The building wall envelope defined by the code is that exterior component, or that series of components that separate the exterior environment from the interior environment, right? To protect us from the rain and from the snow. That's different than the building thermal, or the building wall, the building thermal envelope. The building envelope in that context is talking about the separating of conditioned and or semi-heated spaces, right? So you can have a component, we were in a building yesterday at Monticello, where the building thermal envelope may be different than the building wall envelope because of some open areas and some corridors that don't need to be, conditioned. They can be semi-heated. So again, you can start to see where those two different concepts play. But when we think about what the envelope says, is there certain mandatory provisions, certain installation. If you look through it, the code actually gives us a variety of different expectations that both apply to all compliance paths, as well as when we look at it from the prescriptive compliance process, right? There are certain mandatory provisions like insulation, doors, air leakage, right? And so identifying what is going to be that thermal envelope is critical, so that we know what we're looking for, where we're looking for it. And it would be easy if I was to go and say, this is the building thermal envelope. Well, but what if it's not, right? What if we're not conditioning this entire parking deck, right? And more importantly, what if I'm separating, as we can see in this example here, we've got some bedroom spaces. This is a multi-level mixed use building, right? And so I just took a cut out of it. So it's actually a little bit, there's a tower over here as well. And so if I want to separate these units because I want them to be independently controlled through their heating system, then I'm not just going to have one thermal envelope that's just the exterior, that follows the exterior envelope. I'm going to probably have a series of components to make up and isolate those conditioned spaces, right? So the conditioned space that exists in this unit will be different than the space that exists here. There may even be some separating walls that exist vertically, right? So we're going to have to know where these components are going to be located so that we can properly evaluate them, both in plan review, and plan review feeds our inspection and construction process, right? So we're going to look at considerations, design considerations, such as, again, am I looking at residential controlled space, non-residential space, conditioned space, semi-heated space, and then where is it located within my climate zone? We know that the state modified a little bit this section up here looks a little weird because, again, we know that the locality is a little bit better than we do on a national level. It's easy to draw a line on a national level, and then it's normal for jurisdictions to say, but we're a little bit different than that. And so again, that's just that realization. But we're going to take those two variables, our condition space allocation or design, and our environment, to identify what needs to happen within that those separating elements of our thermal envelope. Right? The code tells us again, we're going to identify these areas that that the determination as to whether a space is semi-heated or unconditioned is approved by the building official, right? Because again, they're the ones, if we have the whole section there for those that want to read the whole thing, but they're the ones who are going to be responsible for identifying these and making sure we don't have uncontrolled designs, right? But ultimately, what we're going to do is we're going to identify, if I have a ventilated attic, that's going to be treated differently than if I have a semi-heated storage space, or if I condition spaces and unconditioned spaces and crawl spaces. So all these components, I need to know, and many of you know, there are some buildings are great, they're boxes. Some buildings are not boxes. And so we're going to have buildings that may look a little different, and we need to know where it is we're expecting to evaluate these components. One of the things that sometimes you'll see, especially in some multifamily residential, is maybe a great, and I was literally just having this conversation right before I got online. Sometimes what we start to see is, as we get people understanding the importance of thermal envelope delineation, representation, you may get pictures or pages in your design that identify your thermal envelope expectations, right? And you can start to see where that envelope is going to be, so that it makes it easier for you to better refine your comments, as well as do your inspections. And so that's, again, whether it's in a normal elevation, whether it's in some type of special page specific to energy code compliance, that's really something that we try to advocate, as maybe it's easier to draw that thermal envelope on its own page. But again, remember that thermal envelope is made up of a variety of different components and expectations, of which we include, obviously, these different features, these different components, and it's all about their role in separating that conditioned space. And it's always insulation, 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 right? Just like Marsha, it's all about insulation, insulation, insulation. It's all about identifying the appropriate material to insulate our walls, our thermal separation. Now remember, while everything begins and ends with the thermal envelope, it doesn't work by insulation alone. Air barriers can't be an afterthought, because air barriers and air movement have consequences, and they affect both our R value, our vapor diffusion, our pollen and pollutants, smoke, smog, and exhaust that manifest, that make their way either into the occupied space or can affect our thermal insulation, depending on the manner in which it's designed. So again, these two systems work in tandem. It's insulation and it's the air barrier. It's the fleece jacket we wear in October, and it's the air barrier that we wear, the air jacket, the thermal jacket that we wear, that we add on top of that insulation when it's December and we decide to go watch a Vikings game, right? When we decide that we're going to go watch a game, then we have all been there. We've gone to football games, especially high school football games in the early fall. Insulated jacket, I'm good, right? It takes the chill off, but I'm not freezing to death. If I wear that air barrier jacket to an actual game in December, whoa, buddy, you see the steam pour out the head, right? And so again, that's the difference between insulation and air barriers. Working together, they control even more the manner in which we heat and control conditioned spaces within that building, right? So that's the idea. That's the visual you have to have in your head. It's insulated, but do I also add in how do I ensure that air barrier also helps to keep that heat inside and not create a moisture condensation issue like I experience when I drive in a car with one of those big jackets on. I about die every time winter comes. I have my jacket, and then I get in the car and we drive for 45 minutes, and I'm like, can I get this thing off, right? Because it traps in that moisture and heat. But remember, not all insulation is created equal. And that's kind of the point of this conversation today. We really want to take a look at the insulation itself. Now remember, you guys are going to get some cheat questions here, but insulation itself does not restrict heat, right? It resists heat conduction, right? It's the thermally charged air trying to move from highest pressure to lowest pressure that causes air to move, right? It's not that the insulation somehow has anti-heating in it. It's that movement of thermally charged air from the interior, hopefully higher pressure inner home to the exterior. Or if we have a higher pressure outside, it's that cold air trying to move into our homes, right? That thermal envelope, that insulation is there to restrict the movement, really the movement of air through that assembly. And that's where we start to test and we get to these calculations, these on what are U values and R values, U factors and R values, right? We've tested the material. We say, okay, this material, and if you watch the testing protocols, what you'll find out is they'll literally put a piece of material inside one of these ovens, and then they'll place sensors on either side as they apply heat. How long does it take that heat to dissipate through that? There's convective heat, there's radiative heat, and there's also convection heat. And so it's determining how much does this insulation, this blow insulation or this fiberglass insulation, slow the transfer of thermally charged heat through that system. And that's how we calculate R values. It's a number of BTUs moving through a square foot of material over a designated period of time. A lot of math involved in it, and that's why we get everything evaluated and certified through the standard, so we know the actual R value of the material. Now I'm going to, or U factor of that material. Now I'm going to tell you, I'm going to spoil alert right now. I'm going to ask the question. We got a few minutes, so I'm going to ask the question. How many of you think we have two values, U factor, R value? How many believe the U, by raise of hand, how many believe the R value is almost like chicken and egg? Which came first, the R value or the U factor? R value, raise your hand. If you believe the R value came up first, raise your hand on our little thing. Okay. If you believe, okay, we're going to put them all down. If you believe the U factor came first, raise your hand. Okay. We got a significant number of people on that side. So the team is right. The U factor came first. And I'm going to give you the trivia question. Well, I'm going to ask, does anybody right off the top, I'm going to give you 7 seconds to answer this. Do you know when the U factor was created or calculated? When did the U factor first come on the scene? Put it in the chat. If you know the answer, when did the U factor first come on the scene? I'll give you 7, 6, 5, 4, 3, 2, 1. We've got two numbers in the chat. We've got a couple numbers in the chat. Got some cheaters in the chat is what I'm going to say, who have heard this before. But in 1701, Sir Isaac Newton came up with a calculation for U factors, right? That's where he came up with the calculation of U factors. So 1701, not 1920-ish. But that was a value that was used to calculate the relative, the percentage of heat transfer through a medium over time, right? The R value, we're just going to, when do you guys think that came out? If the U factor came out in 1701, when did the R value come out? Quickly. 5, 4, 3, 2, and 1. Okay. The R value came into was calculated in 1945. Was the U.S. was returning as the war had just ended, the World War II had just ended. People were building houses and they wanted to have a house that was insulated. Now, I'll tell you right now, I've had many contractors tell me, well, we didn't insulate houses until the 70s. No, we did insulate houses. We just didn't have fiberglass and polystyrene because we didn't have those technologies. But we've been insulating houses for hundreds and thousands of years. Even, if we go back and find some Native American and structures, we can find where they've insulated with twigs and other mediums. But we insulate buildings. And in 1945, the manufacturers of insulation determined that the U factor, which had been their primary source of calculating heat transfer, didn't sound real great, right? Because as Americans, we want bigger, we want better. Bigger always means better. And so every time the value got lower, it was like, oh, we got a lower value. Oh, that's not great. So they sought out someone to calculate a value that increased as the thermal resistance increased, or the thermal transfer decreased, right? So the Professor Everett Schumann from Penn State University took on the charge, divided the U factor by 1, and said, look at that. As the U factor goes down, the R value goes up. And that's how we got the R value in 1945. I have still tried to this day to find out how much they paid him to do 1 divided by U, and I haven't found it out yet, but I'm going to one day. I've asked Penn State for the records. Nobody knows. But again, it was a marketing decision, right? The better the insulation, the higher the number, the better it insulates, right? It's really just the inverse, the exact relationship with the U factor. And that marker there exists at the corner of Burroughs and West College in Penn State University campus. But again, not all insulation is created equal, right? We understand they have U factors, but they also have other functional capabilities. And so when we start thinking about foam board insulation, we may determine that a rigid insulation is more appropriate for our design, not simply because of the mathematical R value per inch, which it tends to get a little bit better, but also it provides a different type of thermal bridging or thermal break when we install it in a type of building, right? If we see that the way the thermal heat transfers through this wood member, remember every piece of wood has its own density, right? If we use southern pine versus redwood, there is a density difference. That's why we use them. We see the different calculations in the building code when it comes to the structural, the load capacity. That also applies to their thermal resistance. And so a southern pine whiteboard is just going to be like an R4 in the wall, right? The heat will transfer through it. If we put this rigid continuous insulation, that thermal insulation, that 2x4 is still going to resist. It's going to still have heat transfer, but now we've got a bridge, right? So maybe we see an R13 with 7.5 versus an R20.5, right? We don't get that thermal connection, the complete thermal loss, thermal path through that 2x4. That's where insulation and continuous insulation starts to come into play. Similarly, we have spray foam insulation. There are 4 types of spray foam. There's sealants, low density, medium density, and roof insulation, roof spray foam. What that really breaks down to is we have 2 types that we usually see in construction. We see open cell and closed cell. Open cell is low density spray foam. It's designed to where as it cures, it remains open. The chemical bond takes place and it opens up into an open cell that allows for air to come in and then fill in those voids. So again, it's filling, the air fills the void. Once that void is filled, it can't accept more air, and that's how you stop the transfer of heat, thermally charged air through that material, right? So it's going into that material and stopping, filling up and stopping, just like fiberglass insulation, right? As the air gets into it, it's now full, and now it can't take any more. By comparison, closed cell cures at a different speed, and so it cures in a way that the chemical that was created the spray foam is still inside that cell. That's why it's closed. And because it's already closed, there's nowhere for the air to get. That's where we get that air permeability rate, right? Well, especially when we think about how we use materials in construction, where we're trying to create we want a material that I don't just have insulation and an air barrier. What if I could find something that did both? Spray foam is one of those options, right? Some types of rigid foam can be that option. And so when we see it in the code, we usually see a closed cell spray foam identified, especially when we think about testing, air barrier testing. We see closed cell 2-pound spray foam at 1 inch. In the IECC, you would normally see it at 4.5 or 1.5 inch, right? 4.5 open cell has the same air permeability rate as a 1.5 closed cell. And so that's where, again, you're starting to see, if I want this material to do this function, have multi-function functionality, then I need to make sure I prescribe the right one. And in doing plan review, if I see the term spray foam insulation, no. Open cell, closed cell. Tell me the thickness, tell me the R value, not just spray foam it. I need to know what it's doing so that I know, is this part of my air barrier? Is this going to be performing some other functionality? And then again, if I'm looking at it from the perspective of, I've got a contract that says I'm doing 19 continuous, and is that spray foam or is that, and then I go in and there's no continuous at all, but they've modified certain values. In a prescriptive compliance, that's a no-no. But in energy cost calculation or maybe performance rating, that may be acceptable. They're evaluating those materials, but I need to know, did that also serve multiple purposes, or do I still have an air barrier somewhere? Do I still have a vapor retarder somewhere? So again, that's why it's important to understand what we install so that we know what it's doing in the field, right? Again, spray foam can do a lot of great things. It can work in relation to other materials, but we also understand, and we've talked about this, the installation of certain types of materials required that we follow certain types of manufacturers' installation instructions. If it tells me I have to have a certain type of substrate, or that there's going to be no moisture on that sheathing, then I need to make sure there's no moisture, right? If it gets applied and it creates voids and pockets, and those are going to either affect the thermal resistance, but also could be spaces. I've seen it happen in roof systems that have been spray foamed, where there's a void develops, and then it gets filled with water and moisture from the roof system, and then we've got to core it out and release that liquid, refill the hole, make sure it properly adheres. I mean, it's always a process. And so spray foam can be used for that bat and flash, right? It can be used in relationship to other materials, but we need to understand how it's installed, and was it installed properly? Because we need to make sure this properly cures and has a good level surface for us to have substantial contact with this bat insulation that we see identified in this image. And again, not every spray foam is there, not every material is there to provide the thermal resistance. And I think that's important to understand, right? We have spray foam for fire protection. We have spray foam or different insulating materials. Thin's glass is a great example. That's for fire resistance. That's not for thermal resistance, but it may play a part, right? And that's where we calculate that U factor. I can decide I've got 1 inch of this and 2 inches of that and 3, and how do they all work together to provide my U factor? So we can have some materials, multiple materials added together to make our buildings even more effective. When we think about insulating materials, I've thrown in some of these slides, different associations that provide great detail, great resources, maybe for design professionals that are online with us today, on maybe how materials work. This one's an example of how does compression, shoving bad insulation into a cavity, how does that affect its R value, right? Because that R value is not from the material itself, it's from its open material stopping the penetration of air. And so if I take what would normally be a 6-inch depth and I put it into an R19, maybe if I take what should be 6 inches to get R19 and I compress it down to 4, I'm now going to have an R14. So how does that compression affect its thermal resistance? And then again, this is the North American Institute of Insulation Manufacturers Association. So this is one of their groups have done the research. Remember, when we talk about insulation and different building components, they want their material to be utilized in our constructions projects. So they're going to have all the details. It's just whether or not we take the time to ask, right? And so that's one of those things. I want to see the details. I want to see the spec sheet on this product, because again, how is it supposed to be installed? We talk about, and again, we talked about air barriers last week. If we're talking about Tyvek is a water resistant barrier when installed and overlapped by 6 to 9 inches, I think it was in our example last week or 2 weeks ago. But if it's sealed and taped, if it's sealed/taped, then it becomes an air barrier. So that Tyvek has interest as a corporation in product, use. But they also know that to qualify, it has to follow these certain protocols. Same thing with insulation. We talked about the ASTM 158 standard, which tells us how we calculate thermal resistance values. Same thing with blow insulation. Now, I gotta always be careful when I say blow, because sometimes I just say blow and I don't say blown in insulation. And so that always causes some confusion, especially when I work with my buddies over at the DEA. I used to work in the court system. And so it's like, yeah, we were talking about blow the other day. Oh, wait, blow insulation. My bad. But again, different types of blow insulation require different types of installation expectations as well as have different thermal resistance values. Not all blow, insulation blow, is the same, right? Fiberglass has a different rating per inch than cellulose, which has a different insulation value from vermiculite. Vermiculite, beautiful stuff. It looks like, but it's also asbestos containing. So we need to understand the materials. Remember, there's a great deal of flexibility when we talk about the types of materials. We could go from fiberglass to rock wool, sheep's wool, mushroom, wood fiber, straw bale, denim. When I first saw denim on a plan, I thought they were going to just take like pairs of Levi jeans and shove them in the wall, right? But no, it's not. Mushroom, when you think about it, when you look at the ES report and the evaluation services report, mushroom has an amazing flammability resistance, right? You can burn fiberglass very quickly, but the flame spread on mushroom is extremely low. And for a material that has the same thermal resistance, it's extremely inflammable. Try and light a mushroom on fire or a compressed mushroom on fire, and you'll see how great it burns. But again, or how hard it is to burn. So again, there's a variety of different materials that we see identified in our codes, and whether that, again, especially in the modern time, we start talking about insulated concrete forms. And one of the things that we need to understand is that minor deviation, minor changes in our design can actually affect how a building is going to perform, right? In this particular example that we've used before and we use sometimes, if I follow this design, right, this is showing us how a wall is constructed from gypsum through the insulation, through the wood, sheathing, wall siding, all that, right? And in this design, we're looking at a 13 bat insulation with a 3.5 continuous. We compare that to a wood frame wall. We would, from a prescriptive concept, if we did the math behind it, we would get to a 0.057. Don't worry, I've already done the math. 0.057 is greater than our maximum U factor for a wood frame wall. 13 plus 3.57 is less than our minimum expectation for insulation. However, making a small change gets me closer and closer to compliance, right? If I go to a 15 plus 3.57, I'm now at a 5.2, a 0.52 on my U factor. Still a little too high, still not all the way there, right? Now I go to a 17 plus 3.57 continuous, right? Now I'm at a 0.48. That 0.48 complies. That's less than my maximum U factor for that wall. So that would comply. However, if I looked at it and compared it to my insulation minimum R value, it doesn't match one of those two values. So I have to remember, am I looking at the U factor or am I looking at the R value? And so if they're providing it as a U factor, it would comply. Okay. Question on the chat. If you tape Tyvek, it becomes a vapor barrier. Wouldn't this then create a double vapor barrier trapping the moisture in the wall? So the concept is the way you're not doing two layers of Tyvek together. No. So you're taking, if you follow the manufacturer's installation instructions, you take your first layer of Tyvek, and then you actually, that becomes your water resistive barrier. And it allows you to seal it. And once you seal it, then you create both a system that creates both a water resistive and a vapor barrier. So then conceptually, you wouldn't be trapping any moisture inside because there's one plane, right? So yeah. But yeah, so if you follow the instructions, it actually tells you. Now, that's the thing. You got to make sure that you pay attention, because some different applications, some different materials, if you look at other house wraps, and I'm just using that one as an example, it says overlap by 19 inches. So it changes the overlap versus taping, right? So you may overlap at 6 inches for a water resistant barrier, but if you overlap 19 inches, then they consider it an air barrier, right? Because they've tested it in those situations. And that's the way you always make sure, if it's something that you're concerned or aren't consistent with, then you want to make sure that you're evaluating how does that match with the ES report. Where's the report that shows this can be utilized? And the vapor barrier has to be on the warm side of the wall. And so you're going to have now remember, we're talking about two different vapor barriers. because you're going to have a warm side that's going to resist vapor transfer from the interior. Because remember, we create vapor inside our buildings now, right? We have inhalation, exhalation. If you've got a 15-year-old, they like to take long, steamy showers. Cooking, just generally, we create vapor. So you're going to have a vapor retarder on the interior wall, which sometimes can be, depending on our classification, could be, I don't remember the classifications off the bat. I know like we could do certain types of paint, gypsum, different types of things. It could be the vapor barrier on the interior warm side, but you're also going to probably have one on the exterior wall to prevent vapor intrusion into the cavity, because that's the problem. We're trying to create a dry cavity and keep it dry, right? And so that's why we're going to resist vapor infusion, and then and so that the cavity stays dry. But again, so what? Sorry, but what I'm getting at is, again, you can play with, the designer can play with the numbers and get a system that allows them. If by the time we get to a 19 plus 357, I'm at a 0.44. If I go to a 20, I'm at 0.43. And when we look at the building, if we look at it from that concept of the other compliance paths, that gives me almost 10 degrees of variance that I can mess with. I can reduce the ceiling and keep the walls. I can eliminate maybe the foundation insulation because I'm using a different wall system. So again, it really gets into why it's important we know what is the compliance path and what is the material doing. Because so again, we've talked about the why, we've talked about the where, we've talked about the what. Now let's identify the how. And that's when the code really gets, I keep going back to this thing, this page. The code provides us this requirement to look at 5.8, which is the product installation requirements. Again, driving back to that, if Tyvek is going to be used, follow Tyvek's installation instructions. If I'm using a different type of house wrap, I'm going to follow that company's installation. One of the things that I've seen more than anything, especially with roof installations, people think that just because I've been doing it the same way and I'm switching one material to the next, I continue to operate the same way. That's not always accurate. Make sure you understand. Make sure your contractors understand how things are supposed to be installed. We've had several problems in some other states that I work in with roof insulation installation. And what they find out is then they start getting all these leaks and penetrations and failures in the roof systems. Well, that's because when you go and actually do the root cause of it, you find out, well, that's not how I always install. I always install it this way, but this is a different material. It has changed. The old, I'm going to be really, it's going to sound weird, but it's going to make total sense. When I got my first iPhone, the button on the side did only one thing: turned on the sound, turned off the sound. This iPhone, I can tell that button to do different things, right? My wife just got a new iPhone last week, and her button isn't even a button, it's a push button, right? It's the same phone, right? But new versions change little things. That's how iPhone sells another version. The same applies to things as simple as bad insulation, or maybe not bad, but the different types of insulation and building components. None of us would agree. None of us, I think, would agree that the 2x4 I get at Lowe's or at Menards today, Home Depot today, is the same 2x4 I would have got 20 years ago. And remember, 20 years ago was 2004. Most of us would not agree that the wood that we got in 1982 is the same wood we get today. Why? Because it's changed. It's still a 2x4, or what we call a nominal 2x4, right? But wood density has changed, the wood's characteristics have changed, and it's not the same. And so that's why we got to think about that. How is it supposed to be installed? What is the manufacturer's installation instructions? And make sure that those projects identify either in the spec sheets or somewhere what are those expectations. Again, from a design perspective, again, I'm making sure that all those features in that building thermal envelope, all these opaque areas that we see identified, are following those tables. Now, again, some of these we're not going to spend a whole lot of time on just because I know we don't have a whole lot of time. but we're also I've got all this stuff in the slides for you so that when you get the handout, you'll be able to reference back to them. And we have more of these conversations. But again, we're separating whether we're looking at the building envelope itself for the whole conditioned space or for the semi-heated space, we're going to be applying those values that we find in the table. Those minimum R values, those maximum U factors for the assembly, right? And again, those are our assemblies broken down again. And then each one of these has, for you that want to look at them, they've got your chapter 6, or not your chapter 6, your zone 6, zone 7 for each of these types of installations, right? And so again, roof is going to have to follow entirely above deck. Are we looking at a metal building? Are we looking at an attic? What are those relative values? And when you actually do the math to calculate some of these U factors, you can actually utilize you'd be able to utilize different types of materials, right? You could get down to a 38. A 38 with 5 continuous would satisfy the attic calculation, the attic U value, would satisfy the insulation fully above deck, right? And a 38 would also satisfy the minimum R value. So again, we're talking about how do we provide flexibility, and what are we going to see? Because again, as technology advances, we're going to see things come in that make us scratch our head and say, does that really match? It can. I've got a product that we were looking at yesterday that was brought to me a couple weeks ago that has a report that represents, it looks like a house wrap that has insulation in it, and it's about the size of a pack of gum or a stick of gum, and it's performing at an R6 based on the standard. So I could wrap a house in an R6 insulation that gives me both my vapor resistance and my insulating capacities. So again, how are these technologies going to advance? And remember, when we're talking about, there's some exceptions for different types of roofs, for steep slopes, ventilated roofs, when we're using photovoltaic, those kinds of scenarios. Also, we know that there are going to be insulation expectations associated with different sky curbs, skylights, mechanical curbs, and other roof curbs, right? Because we're thinking about making sure that we provide that proper R10 when we install these. And that's one of those things that modification and an amendment that took place not only in the roof installation, but also in the HVAC components. Because when we're having rooftop units, we want that raised curb so that we can at least get that R10 into it in preparation for future roof decking, right? Again, the same thing applies to above grade walls. We got those values. The code tells us what we should see, how we would evaluate those. Again, this exception doesn't apply for portions that are above grade and below grade. Do the same thing with below grade installation. Remember, the code, the state's amendment says that we're looking for below grade installation that where the walls are insulated on the exterior side of the wall, right? So if we get a project that looks like this, that's not going to be correct, right? We want to make sure that we stop this concrete from conceptually getting absorbing that heat or that lack of or cool from the exterior. So we're going to put that insulation on the exterior wall to slow the convection, the radiation, the radiant heat from getting to it. But again, that's one of those amendments that this line here that the wall should be insulated on the exterior side of the wall or integrated into the wall structure. So again, we have our floor insulation, we've got our slab on grade insulation. Again, remember, this slab on grade is a little bit different than what some of you may remember from the IECC. In the IECC, it also required for heated slabs to have a layer of insulation under the entire deck, under the entire heated deck, between the heated deck and the soil. That does not exist here. What we're talking about in this R20 for 48, and we had this conversation again yesterday, just to clarify, this is talking about the stem walls going down to the footing, right? So that's the depth, the expectation of exterior mounted insulation down to of insulation down to the footing at a minimum. Well, it goes down until it comes into contact, or the 48 inches, whichever is greater, right? So we want to get at least a 48, but if that's only 36 inches down, 38 inches down, then we stop at 38. We don't have to, obviously, we're not going to extend a footer just to get enough insulation into it. It also talks about the code identifies. Remember, we're talking about insulation. We're talking about doors. We're talking about that thermal envelope. So there are going to be components that maybe have different types of insulation that we don't necessarily see, but we think about in the context of how a door is evaluated. When do we pick this type of door? What types of U factors are we associating with these materials? And again, remember, we're looking at a variety. When we talk about insulation, we have got instructions on what should be on the plans and in the doc and during the inspection in four different locations. 5.4, the mandatory for all compliance paths. 5.5 for prescriptive, 5.6 when we're talking about building trade-offs, 5.8 on installation. And again, so all these different components add into, snowball or layer on top of one another. And again, we have a variety of different expectations when it comes to documentation of our labeling of our materials. When we start to talk about loose fill versus baffles and how they should be installed, substantial contact versus maybe if it's designed to have an air gate space between it and the different materials or surfaces, that has to be preserved. There are grading expectations on the installation of this material. And so, again, one of the things that sometimes gets drawn out and we find in a spec book, but we want to make sure it's still there, is a lot of times in the spec book, it'll say that this is going to be installed at a grade 1 installation. And so we want to make sure when we're doing our plan review that is at least called out at some place, so that we know the level of installation installation expectation for our insulation. Just so you know, there is currently some conversations in the standard development community to modify this to remove grades 1, 2, and 3 and only put properly installed or improperly installed. That'll be an interesting conversation. It's already been sent back for review once, and so the next, I think, it will come back for public comment sometime in October. So again, something to keep an eye on. Remember, when we talk about in plan review, we see receptacles installed inside our materials called for installation in our thermal envelope. We need to make sure that we have adequate either specifications or notes that say when we're installing recessed equipment in thermal envelope walls serving as thermal envelopes, that we protect it for air infiltration, and that they're designed for installation in contact potentially with insulation. IC rated fixtures is what we think of, right? We understand that lighting fixtures have to be IC rated for contact with insulation so that we don't create potential fire hazards. And so the same kind of concept applies when we start talking about certain types of, receptacle boxes and those kinds of things. Are we making sure that they're properly sealed both for air and for insulation contact? Protecting our insulation is important because it won't work if it's not properly installed. And we need to make sure that when we install it properly, and that we consider how those joints are going to overlap so that we don't have air infiltration. If all the joints were the same, that air is going to move right through it. And then again, air resistance is where we get our thermal resistance. And so by staggering it, we're hopefully slowing. Air's not smart enough to know, take a left turn and we'll get out, right? Air's not smart. And sometimes we need to remind ourselves of that. So again, there's a variety of different things that we can talk about, making sure that all this is provided in our documents, that when we go to do our review, we're evaluating not just the symbols, right? Sometimes the symbols that we see don't correlate to the value, and we want to make sure that we identify those materials, right? We want to make sure that we're getting the right equipment called for. And when we look at something like a ComCheck report, we're going to see the values identified. And we want to make sure that those values actually are identified on our designs. Am I seeing an R30 bad insulation? I see an R19. Well, does that match? R19 with 7.5 continuous. I've got an R19 and then I've got a 1.5 continuous. Well, what does that mean? I need an R value. So that's how we're going to compare those two to make sure that our values all match. Again, today was one of those conversations that we really kind of get into that idea of what are we looking for when we do plan review. Maybe I didn't have enough time to get into all the different examples. But next, in 2 weeks, we're going to do another course on plan review. We're actually just going to take the plan itself and walk through a couple of different variables. We're going to take a convenience store, a couple of bigger buildings, and do an actual plan review walkthrough for energy code compliance. Remember, if you have any questions, feel free to check out our website. You can find a lot of different information there, as well as our upcoming trainings for both our in-person and our virtual trainings. Our next in-person is going to be in Fergus Falls on the 27th. I did double check that is the right date. But remember, if you do have any questions or you need some questions answered, feel free to reach out to us in the code helpline. That's going to be a resource for you and the building community or the design community. They can ask questions, and a subject matter expert will respond back with the code references specific to Minnesota's building codes. And as always, one line too fast. If you have any questions, feel free to reach out to us. I'm going to finish. I got another class coming up here in about a half hour, and then I'm going to start sending out our CEUs and updating our rosters from there. So if you have any questions, if I don't get your number, let me know, and I will make sure that we get you properly registered and recorded in the DLI registers or the AIA. If you're an architect, feel free to send me your AIA number, and we can figure out how to get that information into the system for you. I appreciate you guys sticking around. If you have any questions, feel free to send me an email, and we'll see you again in about 2 weeks.